In the last video, we introduced gravitational potential, and I was very excited to explain that topic and to explain why is it actually negative. And I hope by now you understand what it actually is. If you didn't, go back and watch that video because you can't understand this one without understanding that one. Okay, so we need to understand what gravitational potential energy actually is. Now, we now understand what gravitational potential is, and I hope you understand because I tried my best to explain it. We can now move on to understanding what gravitational potential energy actually is. Okay, so gravitational potential energy is defined as the work done to just bring a mass from infinity to a defined point. It's not the work done per unit mass, it's just the work done, period. Okay, so essentially the force times the distance. So that's what gravitational potential energy actually is, right? So it's essentially gravitational potential energy is basically the force times the distance only. Okay, so it's like taking gravitational potential, which is just Fr over m, and then multiplying that by m so that the m's cancel out and you're left with phi m. So in terms of phi gravitational potential energy is just the product of gravitational potential and mass, because it's just the force times the distance that has been moved. So since we know that phi is gm over r, which is over here, and you multiply that by m, we can therefore say gravitational potential energy is actually negative gm m over r, where m is the mass of that small little object that will be in discussion. Now, this is very interesting for you to explore, because if you take the mass of the Earth, mass of that little person, and you apply that equation, you can find the potential energy that is possessed by the object at a specific point in time. And it's very important for you to be bearing that in mind. So we could have been taking a different route of integration to explain why we're arriving to this point, but I don't want to bore you guys. It's going to be extremely complicated. You can look that up. There are multiple videos online that can help you understand how to integrate and arrive at that equation. I've linked some of them in the description below. But essentially, that's an equation for gravitational potential and energy. And questions can ask you, hey, explain or state that equation in terms of phi and m, right? So EP is equals to phi m. Sometimes the negative is included if phi is actually given as negative phi, right? So EP can actually be negative phi m in that regard. So now we understand what gravitational potential is and what gravitational potential energy is. We now need to derive an equation that we have seen every single day. And we're like, hey, gravitational potential energy is mgh. So if you didn't understand, where does it even come from, and you're curious to understand why that's true, welcome to this video, and we're going to explore that together. Okay, so gravitational potential energy, mgh, that equation comes from you moving a specific distance h above the Earth's surface. So at the Earth's surface, EP is equal to negative gm over r, right? Fairly simple. If you move a specific distance h, r plus h is going to be the new distance where you're at. So the potential energy at that point will be negative gm m over r plus h. Hope that makes sense. Okay. So we need to sort of understand, how do you find change in the gravitational potential? And you need to know this equation because it's going to come a lot in some of your calculations. So it's equal to the final potential. So potential is represented by U. I'm going to represent potential energy by U. Gravitational potential is represented by phi. Gravitational potential energy is represented by U. So delta potential energy is actually final minus initial. So we now know that the final is actually negative gm over r plus h. Subtract negative gmm over r. So negative and negative gives you a plus over there. So this will be the equation for delta U. So we can easily factor out gm over r. We're left with 1 over r plus h minus r plus h. And we take r plus h. So r times r plus h. We take that as a common denominator and we put it down at the bottom. So if you say r into r plus h is going to be r plus h, which is over there. And if you say r plus h into r plus h, it's going to be r. So 1 times r is going to be r. So we have r plus h minus r. So r minus r is just 0. We're left with delta U being gmm over h over r plus h. And you can see these in the negative sign because we've dealt with that. Okay. But we can safely make an assumption that the distance h that we're moving is going to be very small, guys. Remember, if you're moving like 30 meters, right? And the radius of the Earth is 6,400 kilometers, it's not going to add up. So essentially, we can assume that r times r plus h is approximately equal to r squared. Okay? Like this, right? So the height h is less than r. Hence, the following generalization can be made from that above statement. Right? Delta U will be equal to gmm h over r squared. So instead of that, we can now have, replacing r plus h, we can replace it with r squared. Okay. So we'll then end up with g is equals to gm over r squared, which we already know. We plug that in, we remove gm over r squared, and we're just going to have g taking that place. We'll end up with mgh, right? So it's important for you to understand that r plus h is approximately equal to r squared, right? Which is over there. I forgot that squared over there. Or r plus h is just approximately equal to r. So either way, we end up with r squared. And this is where we get this equation over here. So questions then ask you, hey, can you state and explain why the change is actually given by that expression? And you must actually be able to do that, as I've just demonstrated. But in a nutshell, you need to understand, hey, the energy is here at this point, is now that at that specific point. Final minus initial, do the algebraic manipulation, arrive at this equation, make an assumption that r plus h is the same as r squared, because the value of h is extremely small. So we can replace that with r squared. Know that gm over r squared is actually g. So we'll now be left with gmh or mgh for short. So that's where the equation that you know that's popular, mgh comes from. And we use it to find gravitational potential energy that you have gained when you've moved a specific distance h. Because we have to gain energy as we move